Alright, so we are now going to start today's lecture on chemical reactor theory. We'll start a new module today, and that's gas liquid reactions. Okay, so in the last three modules, including this module, what we are looking at is basically multi-phase reactions, gas solid or liquid solid catalytic reactions, liquid solid or gas solid non-catalytic reactions, in which the solid itself undergoes a change. And then in this case we are going to look at fluid reactions. We'll take gas liquid reactions, but it is also applicable to liquid liquid reactions. So for example, if you have reactions taking place between a component in an organic phase and another component in aqueous phase, the analysis that we are doing over here is applicable for those situations as well. Okay. Just to remind you, in this set of modules we are looking at the mesoscopic analysis. That means we are looking at either a single particle within the reactor, or a single bubble within a liquid, or a single drop within a gas, or it might be a film, and then you might be looking at one layer of the film. Okay. So we are not looking at the entire reactor level what happens. That is something that we will start looking at from next week onwards. In this particular four and a half weeks, what we are looking at is really the mesoscopic analysis. Okay. So again, when it comes to gas liquid reactions, we are going to look at either a bubble or a droplet or a film, and a small part of that is what we are going to use in order to do the analysis. Okay. How that affects when this reaction happens in an entire reactor is something that we will talk about in the 9th module. Okay. Alright, so further reading would be Froment and Bischoff chapter 5, okay, and the originally all the things that I have in these notes, originally it came from Doraiswamy and Uner's chapter 10 primarily, but 6 and 10. Okay. So I have since modified it based on the inputs from students, because students prefer to have one textbook. So in the first half of the course, where I could use Davis and Davis, I have used Davis and Davis, so that's a little bit easier textbook. Again, I don't necessarily find Davis and Davis more easy or more difficult, but students have said that they found Davis and Davis easier than Froment and Bischoff. So for the first few modules, pretty much until module 5, we have used Davis and Davis, and this point onwards we are primarily going to switch over to Froment and Bischoff. The analysis in Doraiswamy and Uner is much more richer for gas liquid and gas solid reactions, and the reason also is that when Professor L.K. Doraiswamy was in NCL in Pune, a whole lot of his work focused on multi-phase systems. Okay. A lot of his work focused on gas liquid and liquid solid systems, and therefore his book, so there are a couple of books. One is a very classical book, but it's no longer in print, but it's a little bit difficult book to read, and that's Sharma and Doraiswamy. And this one is a little bit more geared towards students. That's really geared towards practitioners. This one is geared towards students, and it's a very nice resource material to have if you are looking at multi-phase systems. I am saying that because there are several faculty in our department who look at multi-phase systems, and if you are interested, so that would be either Professor Pushpavanam, Professor Ranganathan, could be Professor Swapna, Professor Himanshu, somewhat in my group. Again, experiments are done by Professor Rajneesh, but we work together for simulation of this system. So if you are working in any of these groups in multi-phase systems, the couple of books to look at is Doraiswamy and Uner, if you're more experimental or simplified analysis, the CRE type of analysis. If you are looking at CFD type of analysis, then the other book that we have used in our course, very first module of our course, okay, Jacobson's book. and Jacobson's book is really bird Stuart Lightfoot for reaction engineers. Okay, so it's really transport phenomena book, but the focus of the transport phenomena type of material that Jacobson covers is on the reaction part. Okay, when it comes to CFD, the reaction part is called a source term or a reaction source term. So Jacobson spends a lot of time on this source term. What I mean by that is, if you look at your equation, you have dC by dt, that is a transient term. This is the convection term. This is the diffusion term. This is the source term. Okay. In general, this is written as sigma, and one part of that sigma might be reaction. Okay. It might be disappearance because of some other reason also. Maybe there is a wormhole in the reactor and the material is just disappearing through that wormhole, but I mean, of course, I am joking. But source term basically means anything that happens within a control volume because of various factors. So, for example, when it comes to heat transfer, a common source term would basically be or energy balance. So, heat rather than heat transfer, more appropriate term would be energy balance. There would be kinetic and potential energy, right. So, if potential energy would be an energy source term in sigma. If there is radiation heat transfer will come in sigma. If there is heat of generation or release because of reaction, that will also be captured in sigma. So, sigma captures multiple things, not just the reaction term, and that is what Jacobson book focuses on, and therefore, if you are going to work with someone like Himanshu or Swapna's group, this might be a good resource to have. It is not really a textbook, but it is really a resource material. Okay. So, that is about how do you go off from here after the course is over. Let us come back to this particular module. As I said, that we are focusing on mesoscale in modules 5 to 7. Conditions might vary around the reactor in the macro scale, and at the micro scale, the rate of reaction forms the input for the mesoscale that is done in this module. Okay, that is how these three modules connect with what you have done in modules 1 to 4 and with modules 8, 9 and 10, what you are going to do. Okay, so, this is kind of a connecting layer. When it comes to homogeneous reactions, you do not really need to think of the connecting layer too much, but when it comes to non-homogeneous, any kind of a heterogeneity is there, you need to think about that connecting layer as well. Okay. Yeah, in all your undergrad, you had pushed that connecting layer under the carpet. We are going to, hopefully we will have enough time to remove that carpet and bring that connecting layer in the last week of this course. Okay. So, what did we do in the previous module, or actually the previous two modules? Okay. We considered a diffusion and reaction taking place within a particle. Okay. Now, within a particle there was external diffusion, there was internal diffusion plus reaction, and we talked about how to handle all of those cases. Okay. In module 5, only the fluid phase was reacting. Okay. So, nothing really changed with time and so on when it comes to a catalytic particle. All that happened was with the gas phase species A only. Nothing really happened with the solid phase species, right. So, that was what we covered in module 5. Okay. Now, when it came to a particle, and then let us just expand this to more of a composite particle. Okay. Let us say you have an outer particle, you have let us say a middle particle, and let us say you have an inner particle. Let us say there is also a gas film. Okay. So, in the gas film you have basically that is the flux. Okay. This is in moles, and you can multiply it by that is going to be the flux through the system. Okay. Now, if it is the first shell, let us say the first outer part, if there is reaction not taking place in the system, we are going to have 0 equal to del square C. Okay. Or if there is reaction taking place, it is going to be plus R1. Okay. Likewise, we can have the middle part, and the middle part is 0 equal to del square C, or again 0 equal to d del square C plus R2. Okay. And same thing for the central green also. Okay. There were 10 layers, we will have 10 such reactions. Okay. Does not matter how many layers there are, right. Now, what do? You have boundary conditions at the two boundaries, and the boundary condition is that the Ca over here is CaS2, Ca over here is CaS2, Ca over here is CaS3. Okay. So, Cab is known, okay, but CaS1, CaS2, CaS3 is not known. Okay. So, what do? You do the flux matching. Okay. Now, how do you do the flux matching? The flux that comes in minus flux that goes out is equal to rate of reaction. Okay. Flux that comes in minus flux that goes out is equal to rate of reaction. Flux that comes in is equal to the rate of reaction inside this green. Okay. So, this is exactly what we had done in yesterday's class. Okay. Over there, the outer shell, there was no reaction, middle core there was a reaction. So, in was equal to out for the outer shell. Okay. That is how we did the derivation towards the second half of yesterday's class, right. Those are the equations that you use in order to get rid of those unknowns. Okay. That is called flux matching conditions. Okay. Something that we have done 3-4 times, and again, I mean, you will not get a complex particle like this usually in your research or in a course, but if in case you get the a particle that is complex like this, you have all the tools to address a situation. Okay. They are nothing but what you have been doing over the last 3 weeks. Okay. Now, this takes care of the one part of the problem, and that is basically the gas phase or the fluid phase. But in module 6, you had giving product. Okay. And in this case, there were two possibilities. Okay. These two cases. Okay. For this case, we looked at the solid dissolution model. For this case, we did the shrinking core. Okay. If you look at Doraiswamy and Unner, you will see that there are a few other situations also, that is where the porosity kind of changes in the overall system, the properties of the core and shell changes as the reaction take place, all of those situations are there. none of those we can really deal with in a pen and paper course like this. Okay, those all require numerical simulations in order to analyze them. So therefore, those are the cases that we have not covered. But again, that is not what is happening in the gas phase. The gas phase analysis remains similar to what you did in module 6, sorry, module 5. In module 6, there are two parts to it: what happens to A and what happens to B. Okay. Rate of reaction that is taking place is the same for A plus B going to products. Okay. If R is the rate of reaction, if it is A plus B going to products, if R is the rate of reaction, the rate of consumption of A is minus A multiplied by R, rate of consumption of B is minus B multiplied by R, right, something that we talked about right in the beginning in module 1. Okay. Same concepts are going to be over here. Okay. And you have d by dt of the total number of moles of B is going to be equal to rate of reaction multiplied by volume area of cross section, whatever the case might be. Okay. In the right hand side, R comes from what we did in the previous slide. Okay. And volume is basically pi r cube. Okay. What if this was not a sphere? If it is a slab, is ACS multiplied by L. Okay. So, let us say that this is the slab that is getting reacted, this is your ACS. Okay. L, if this is a slab that is present in the flow, L is going to be half of the thickness of the slab. Okay. And as the reaction takes place, maybe the L is going to get reduced. Okay. If a slab is like this, how is the dissolution going to happen? Dissolution is not going to happen like this. By the time this front has moved to, let us say, this particular part, that curved part of my phone, this front would have already moved and this solid would have dissolved. Okay. So, what do you consider as a slab in this type of a situation, where this thickness is much lesser than this length? Or more appropriately, this cross sectional area is much larger than either this or this cross sectional area. Okay. That is how you want to analyze the slab. If this is a slab in the fluid, okay, half of this is your L. If this is a slab where only one side is the fluid, the entire thickness is your L. Okay. That is for your convenience. If you want to take entire thickness as L and do the analysis, all the analysis works fine as well. I am just talking about how the analysis is done in your textbook. Okay. When it comes to your assignments or your exam, the context will make it very clear which one you want to, you need to use. Okay. Okay. All right. And again, I keep saying this because different books treat L differently. R is very straightforward because it's just a sphere. So, all textbooks treat R in exactly the same way, but when it comes to the analysis, your Froment and Bischoff and your undergraduate textbooks treat L slightly differently, and that is why to avoid any possible confusions, or I am just discussing this. Okay. So, now coming to module 6, what is the difference? This particular, all these circles that I was showing you, right? This circle in module 7 is not a solid, but it is a fluid. So, this might be a liquid and there might be a gas outside, or the other way around. Okay. So, that is the kind of situation that we are going to consider. Okay. So, you can have, for example, a gas bubble that is rising in a liquid, you can have liquid droplets that are falling in a gas, okay, or you can have a falling film. Okay. Just as we had done in module 5 and 6, we will take a binoculars. This does not look like a binocular, it more looks like a lollipop, but whatever. Take that binoculars and zoom in at a droplet layer level, or zoom in right at the boundary of the film. Okay. And zoom in at the boundary, this is the interface. Okay. For simplicity and whatever, I will or to make it consistent with your textbook, I will consider liquid on this side, gas on this side. Okay. Now, we will assume that it's the A in the gas phase, the reaction is going to be okay, but the reaction usually does not take place like this. Most often its A will get dissolved in the liquid, then will react with B. Okay. Or sometimes its B in the liquid that might get evaporated into B in the gas phase and undergo the reaction. Irrespective of whether it is B going into the gas phase and undergoing reaction, or A going into the liquid phase and undergoing a reaction, or A and B both being liquids and liquids, and therefore one of them dissolving in the other liquid and undergoing a reaction, all three cases the analysis remains the same. The results will differ slightly. The results will differ slightly not because of any difference in your analysis, but because of the difference in the magnitude of the parameters. For example, diffusivity in liquid phase is of the order of 10 to the power minus 8. diffusivity in the gas phase is of the order of 10 to the power minus 5 meter square per second. Okay. So, diffusion in gas phase is 3 orders of magnitude faster. Density in the gas phase is 2 orders of magnitude lower. Okay. Those are the things that cause difference in the observed behavior, but our analysis and how do we look at a problem like this and how do we come up with the expressions and so on does not change very significantly. It remains more or less the same. As a result, we will only consider one situation, and the situation that we will consider is the situation that happens most often. Okay. So, what we will assume, though the analysis is not restricted to only this situation, what we will assume is that the A in the gas phase dissolves in the liquid, and thereafter A and B that are now present in the liquid react with each other. Okay. And there are various theories about this, and okay, there are 3 branches of theories or 3 major theories. One is called as a 2 film theory. Okay. The other is called as a penetration theory. And the third one is surface renewal theory. Okay. All of these theories treat the interface and the interaction across the interface slightly differently. The 2 film theory, the way it, so this is the interface. The 2 film theory says that there is a film in the liquid phase, there is film in the gas phase. Okay. Penetration theory basically talks about packets of gas that will go and penetrate into the interface, and because of this penetration of that packet of gas, the reactions take place. Okay. Surface renewal theory basically says that there are kind of packets of gas that are present all throughout, kind of like a film, you can say. Okay. As these gas packets get utilized, they get renewed by new gas packets that come in. Okay. Now, the implication of all of this are quite important and quite different. Okay. The 2 film theory results in the diffusion being directly proportional to the mass transfer coefficient being directly proportional to the diffusivity. Okay. The other 2 theories result in a different consequence. It's the mass transfer coefficient is proportional to the diffusivity's square root. Okay. The intricacies of theory and all that are present in your textbook. They are there in Froment and Bischoff. Because of what we have been doing over the last 3.5 weeks in module 5A, 5B and module 6, that is the reason why I will prefer this theory in this course. Okay. What do you mean by the two film theory? Two film theory, we mean in the gas phase, okay, and in the liquid phase, or we will do it slightly differently actually. I will tell you why. Okay. Okay. Do not have to worry about this, we will restart tomorrow's lecture at this point. We are not yet done with the lecture, we have around 10 more minutes. Yeah, but we will have a little bit of discussion about what we have. Okay. So, now the floor is to you. I can guarantee you there will be at least one exam question on examples either from gas solid non catalytic reactions or from gas liquid reactions or from both. Okay, just an MCQ. You had one, the first MCQ last in the midterm was for the catalytic gas solid reactions, right? What reactor can be used. So, examples. Examples of reactors that you know or examples of reactions that you know or you think of. Yeah. Bubble tower. Trickle bed. Okay, and we will again, as we have done in this course, we will broaden the idea of reactions a little bit. Okay, remember start of the lecture I talked about Jacobson's book source term. We in CRE or CRT handle the source term. Source term means somehow that food is disappearing, whether the food is getting in your tummy, reaction, or whether the food is getting in your pocket, not really reaction but mass transfer, it does not matter. So, we will expand the situation to say somehow A and B are disappearing, those might be through reaction or those might not be through reaction. Could be, for example, solid dissolution. So, solid dissolution might be because of a reaction, or solid dissolution might not be a reaction as such, it might just be let us say common salt. If you have a slab of common salt and that common salt dissolving, so NaCl just dissolves in water, well that also you can say is a reaction because it goes to Na plus and Cl minus, but so we are not restricting to reactions in the traditional sense, we are broadening it to the case where one of the species disappears because of either chemical or physical processes. So, anyway, yeah, bubble tower, trickle bed, sorry, spray tower. Yeah. More examples here is good. Okay. You will have these notes with you. Tray column. Reactions. So gas, liquid, liquid, liquid. Gas, liquid, solid is also absolutely fine. Not a problem. Fluidized bed. Okay. You may not have two fluids in the fluidized bed. We are talking about two fluids. Airlift reactor. Anything else? Okay, what type of reactions? What are the reactions that you can think of? In all of these. Hydrogenation. Making vanaspati ghee, that's an example. Hydrogenation of vegetable oil. CO2 capture in liquids. In liquid amine solution, in monoethanol, liquid ammonia solution, or in monoethanol amine, so on. Yeah, I mean this is good enough for us now. So we will consider various cases. So let's look at whether it is SO3 plus water or CO2 plus monoethanolamine. Okay, there is basically a dissolution process and there is a reaction process. Okay, so people look at this in two different ways. Okay, because of mass transfer limitation, the reaction rate is slowed down. That's where the concept of eta comes in. Okay, or other way to look at it is because of reaction taking place. Okay, the dissolution equilibrium shifts towards right, so the dissolution gets enhanced. So there will be an enhancement factor that comes in. Okay, so eta is basically observed rate Okay. So, F is the ratio of the rate of mass transfer, observed rate of mass transfer, which is also equal to observed rate of reaction, divided by the observed rate of, divided by the rate of mass transfer, what it would have been if there were no reaction. So, for example, CO2 will dissolve in water, okay, or CO2 will also dissolve in monoethanolamine, but if it dissolves in water, it remains as CO2 or H2CO3 or HCO3 plus, right. So, that is how it, or HCO3 minus, that is how it actually stays in water, right. But if monoethanolamine is there, the CO2 reacts with that amine. As a result, more CO2 can get dissolved. So, the dissolution of CO2 is enhanced because of the reaction. So, that is captured by the F factor. The reaction is slowed down because of mass transfer limitation. So, that is captured by eta factor. Of course, eta and F, as I am talking about, is for an isothermal case. If there is exothermicity because of reaction, eta can go greater than 1 as well. Okay, we have not really covered that in the class, but if you look at your textbooks, either Davis and Davis or Froment and Bischoff, it's all there in the book. Okay, so this is how we are going to do the analysis. The analysis is going to follow on the same principles or that we have done in module 5 and module 6, where we are going to look at films and the reaction taking place in one of the films. Okay, the reaction, for the case of simplicity, we will say that the reaction is going to take place in liquid film. Okay, and after the dissolution of A in the liquid film, oops, I should have, my mistake, this should be CB. Okay, this is how this goes. Okay, now don't misunderstand this as partial pressure is lower than concentration. How is partial pressure lower than concentration? Okay, why is that? So don't interpret this as partial pressure being lower or higher than concentration. Why am I saying that? What is the units of pressure? Pascals, bars and so on. What is the unit of concentration? Moles per meter cube or moles per centimeter cube. Okay, so the y axes are different for the light blue and dark blue. Okay, so there are two y axes, one y axis is for pressure, another y axis is for concentration. Okay, so just because visually you see CA at a different location, it has absolutely no meaning. I just drew CA at a different location because I didn't have space. Okay, so please remember that. Okay, and the reason why instead of kg multiplied by CAB, I used kg multiplied by PAB is because I am going to use concentration Ca for the liquid phase. No other reason. I could have always said kg multiplied by CABG minus CAIG. Okay, and how is CAI and PAI related? The Ca in the liquid phase and Pa in the gas phase, how are they related? Not ideal gas law. Interfacial, what would be the interfacial relation? Henry's law, for example. Okay, they would be related by Henry's law. And if P is related to C by Henry's law, P by RT is also related to C. So you can use Henry's law to relate concentration in the gas phase with concentration in the liquid phase as well. Okay, so we will start off from here. We will spend 10 minutes to go over the two film theory basics and so on before delving into the derivation in the next class. The class after that will be a tutorial, and then next week we will come back and do rest of the derivation. Okay, so just a slight change that we have started doing from module 5B or after your quiz is to do a tutorial before finishing off the derivation. Okay, all right. Thank you very much.